Hey, this is Mr. Ariel, and I'm here today with a lesson about isotopes and average atomic mass. Let's go ahead and get started. Now you should have a worksheet to go with this video, and the first part we need to fill in is up at the top that isotopes are atoms of the same element with a different number of neutrons. I think you got that idea in a previous set of notes, but now we're just going to expand on it a little bit. So for the example, I left you a space on your sheet. Carbon-12 is also written as C-12, and we know from this number right here, or this one right here, that its mass is equal to 12. Now there's another isotope of carbon, it's called carbon-13, and it has a mass of 13. But the issue we're going to explore today is why does carbon's atomic mass, on the periodic table, the average is 12.01. You don't have to copy this periodic table into your worksheet, I'm just putting it up here for illustration. And so what we're going to learn about today is a concept called average atomic mass. And that's a weighted average that takes into account the relative abundance of each isotope. Like this carbon-12 over here, it makes up 98.9% of all atoms of carbon pretty much in the universe. And then carbon-13, that only makes up 1.1% of the atoms in the universe. So you can tell that carbon-12 is much, much more abundant, and that's why the average atomic mass is very, very close to 12, but not exactly 12. So if you've got this part on your worksheet written in, let's move on. Now I put it in a different order on your worksheet. I actually have the formula up above the practice problem, but I moved it for the video just to make it flow a little bit better. So we're just going to do 3 practice problems here, and the first one says carbon has 2 naturally occurring isotopes, carbon-12 and carbon-13. Carbon-12 accounts for 98.9% of the carbon in the universe, and I guess we already got this part too. Calculate the average atomic mass of carbon. And so here's the formula. It's on your paper. It's not something you have to memorize. You'll always have access to this information. Now the part you might not know in math is this symbol right here. It's called sigma. It's a Greek letter, and it means the sum of. And so literally this is the sum of everything that comes after it in the formula. And so let's just see how that works. The average atomic mass, I'm just going to call it the average mass to save a little bit of writing, that's going to be equal to the sum of the relative abundance of isotope N. And so for that, we just go back and find the relative abundance of our first isotope, that's carbon-12. So I'm going to say that that is 98.9%. But if we're going to do this math, we have to do percents as decimals. So 0.989 multiplied by the mass of isotope N, and that's 12. Now back to the sigma notation, it's the sum of everything in this formula. And isotope N, well, we have that one, that was carbon-12. And so now we need to add on carbon-13. We have to basically repeat the process so that we've got all of our isotopes accounted for. So we need the relative abundance of that element, and so that's 1.1%. And so that's decimal form. We need to move that decimal 2 spaces, and so that's 0.011. And then we'll multiply by the mass, that's carbon-13, and we'll do it like that. So to finish up the math on that, this first part works out to be 11.868. And then the second part works out to be 0.143. And if you add those together, works out to be 12.011. And that's atomic mass units. And lo and behold, that's exactly what you find for carbon's average mass on the periodic table. So if you've got this practice problem, I'm just going to move on to the next one. And for this one, I challenge you to try it yourself. It's going to be the exact same process as problem 1, except for the fact that we have 3 isotopes to deal with. So pause the video, give it a shot, and come back. Now for this one, I'm actually going to work out all the steps in case you're struggling. We've got the average mass of neon, and that's going to be equal to the sum of this statement, but we have to repeat it 3 times. So let me just go ahead and add that in. We've got a parentheses plus another parentheses plus a last one for that third isotope. So my first one is neon 20, that's 90.5%. So I'm going to move that decimal, 0.905, and I'm going to multiply by the mass of 20. And so just for clarity, this is neon 20 right here. I'll go ahead and set up neon 21 right here, and this is neon 22. So neon 21, has an abundance of 0.25, but I need to move that decimal. So that's, let's see, 2 zeros, and then the 25, and we'll multiply by our mass. And then finish up, neon 22 makes up 9.25%. So if I move that decimal, we got that right there, and then that's going to be times the mass. So going to the calculator, the first part works out to be 18.1. Then we add on let's see, 0.0525. And we're going to add that last part, that works out to be 2.035. So with that, the average mass of neon just works out to be 20.18, and those are atomic mass units. Now if you check out the periodic table here, that's pretty much what neon's average atomic mass works out to be. This one doesn't line up perfectly with neon because it probably has more than 3 isotopes, and I just kept the problem kind of shorter. If you've got this written down, let's move on to the third problem. We've got rhenium as one of the rarest elements on Earth, and we know the average atomic mass of naturally occurring rhenium is 186.21. We have 2 common isotopes, rhenium-185 and 187. And for this one, we want to calculate the percent abundance of each isotope. So here, we're going to use the formula, but we know this number right here is 186.21. And so now we're going to set up the formula just like we have done in the past. It would be the 2 isotopes, and this one's going to be rhenium-185, and this one will be rhenium-187. And we know that the mass of each one, that's 185, and this is 187, but we're simply trying to find the abundance, the percentage that each isotope makes up. And if you're looking at this equation right now, you might be saying, I don't know how to solve an equation that has 2 different variables. I mean, I could solve for x, but the answer would have y in the answer. And so how do you do that? Well, we're just going to use a little trick that the relative abundance, the percentages, the relative abundance of element x plus the relative abundance of y, that has to be equal to 100%. But remember, for math that we're going to do, this has to be written as a decimal. And so we're simply going to say that x plus y is going to equal 1. Now, if you just do a little bit of algebra that I know you know how to do, we can say that y is equal to 1 minus x. So what I'm going to do now is take this 1 minus x, and I'm just going to simply plug it in right here for y. Let me go ahead and write that again. It's a little bit easier to see if we just go ahead and fill out the math. And I'm going to simplify this part, that's 185 times x. And then I'm going to add on this part, and so here is where I'm putting in the 1 minus x, because that's what we're saying is equal to y. And so we still got to multiply by 187, so close that parentheses. Now I'm going to rewrite it one more time. That's still 185x. And then now we need to distribute, so that's going to be plus 187, because 187 multiplied by 1, and then we're going to subtract 187 times x. So let me simplify that one more time. 186.21 is equal to, let's see, 185x minus 187x. That's just negative 2x. And then we have still plus 187. I'm going to subtract the 187, and of course that goes away. And so the left-hand side, if I plug these numbers in a calculator, that works out to be negative 0.79 is equal to what I have left is negative 2x. Let me scroll the board just a little bit. I can finish this up. I can divide through by negative 2. And of course that cancels out. And so I'll finish it up over here. X is equal to negative 0.79 divided by 2. And that just works out to be positive 0.395. Now, if you lost sight of the goal, we were trying to find the percent abundance of each isotope of rhenium. And so back up here, we called rhenium-185, we call that X. And if we move that decimal back to percentage form, that means rhenium-185 is 39.5% of the atoms of rhenium. And if I use that idea that X and Y, the 2 isotopes, they have to add up to 100%, well, then if I take 100 and subtract off the 39.5, that means rhenium-187 is just 60.5% of the atoms of rhenium. Now, if you've got this problem written down, you're all done with the video. I hope the video was helpful to you today, and as always, thanks for watching.